How does a single loose wire slip through layers of inspections, automation, and safety protocols inside a modern factory and still manage to trigger a full-scale industrial disaster? That question haunted investigators long after the alarms stopped screaming and the production floor went silent. Because this was not an old, decaying plant running on outdated systems. This was a state-of-the-art facility, designed to be resilient, efficient, and supposedly immune to human oversight. On paper, everything looked perfect. Redundant power lines, smart sensors monitoring voltage, temperature, and vibration in real time. Automated shutdown systems calibrated to react in milliseconds. Engineers trusted the system so deeply that small irregularities were treated as noise, not warnings. And that confidence became the first invisible crack in the structure. The wire itself was insignificant at first glance, thin, ordinary, hidden inside a junction panel rarely opened once installation was complete. It was not supposed to move. It was not supposed to loosen. It existed to carry a low-voltage control signal. Nothing dramatic, nothing dangerous. And that assumption is exactly what allowed it to remain invisible. No one expected a failure there, so no one truly looked. Days before the incident, subtle signs appeared. A brief flicker on a control screen. A sensor reading that momentarily fell outside its normal range, then corrected itself. Operators noticed, logged it, and moved on. The system stabilized. Production targets were being met. Stopping the line for a deeper inspection would cost millions. The data said everything was fine, so the human instinct was to believe it. What no one realized was that the loose wire was behaving unpredictably. Each vibration from heavy machinery caused microscopic interruptions in the signal. These interruptions were too fast to trigger alarms, but frequent enough to confuse automated controllers. Systems began compensating for problems that technically did not exist. Corrections stacked on top of corrections, silently pushing the operation closer to instability. Inside the control room, dashboards still glowed green. The factory looked calm, but beneath that calm surface, logic loops were colliding. Safety systems were preparing to intervene without fully understanding what they were reacting to. It was not chaos yet. It was something more dangerous, false stability. Then came the moment when vibration, load demand, and timing aligned in the worst possible way. The loose wire broke contact for just long enough to send a corrupted signal through the network. Controllers interpreted it as a critical fault in one subsystem and a normal condition in another. Two automated responses activated simultaneously, each trying to correct a different version of reality. From that point on, events moved faster than human reaction time. Machines accelerated when they should have slowed. Valves closed while pressure continued to rise elsewhere. Emergency protocols triggered, but not in the correct sequence. The factory was no longer operating as a coordinated system. It had fractured into isolated components, each following flawed instructions. Operators saw alarms cascade across their screens, one after another, too quickly to process. Training did not cover this scenario because no one imagined such a failure path was possible. The wire had never been considered a critical risk. It was not listed as a single point of failure. Yet in that moment, it became exactly that. This is where the disaster truly began, not with an explosion or a fire, but with misplaced trust. Trust in automation. Trust in design assumptions. Trust that small things cannot bring down massive systems. And as the factory crossed the threshold from controlled operation into runaway failure, there was no simple way back. Before we continue, there is something important to reflect on here. At what point does efficiency replace vigilance, and how many other systems around the world are operating under the same quiet assumptions right now? If this story is already making you rethink how fragile even the most advanced industrial systems can be, take a moment to get involved. Leave a comment below. Sharing your thoughts on what you believe really turns a small technical flaw into a massive disaster. Understanding these failures is critical, not just for engineers, but for anyone who depends on modern industry every single day. If this analysis is valuable to you, hit the like button and subscribe to the channel so you don't miss the next part of this investigation. The factory where this disaster unfolded was marketed as a benchmark of modern industrial automation. From the outside, it represented the future: minimal human intervention, self-correcting systems, predictive maintenance powered by data, and a control architecture designed to eliminate human error. Engineers spoke proudly about how few People were needed on the floor. Decisions were made by algorithms. Reactions happened faster than any human could respond. And that belief, that automation equals safety, quietly shaped every choice that followed. Automation did not arrive all at once. Over years, manual processes were replaced piece by piece. First, monitoring, then adjustments, then decision-making itself. Humans became supervisors instead of operators. Their role shifted from actively controlling machines to watching dashboards and trusting alerts. When everything works, this feels like progress. When something breaks outside the model, it becomes a trap. Inside this factory, thousands of signals moved every second. Voltage levels, temperatures, pressures, motor speeds, load balances. Each subsystem had rules defining what was normal and what required correction. But no system truly understood the whole picture. They only understood their slice of reality. The assumption was that if every subsystem optimized itself, the whole plant would remain stable. That assumption ignored a fundamental truth of complex systems. Local optimization does not guarantee global stability. When one automated controller compensates for a perceived problem, it can create stress elsewhere. Another controller reacts to that stress, and soon the system is no longer correcting reality, but reacting to its own reactions. This is where automation stops being protective and starts becoming dangerous. The factory relied heavily on redundancy. Multiple sensors measured the same variables. Backup controllers stood ready to take over if one failed. Power feeds were duplicated. On paper, this meant resilience. In practice, it created complexity. Redundancy only works when failures are clear and isolated. When a fault is ambiguous, redundancy can multiply confusion instead of resolving it. The loose wire exploited that ambiguity perfectly. Its intermittent behavior did not trigger a clean failure, produced conflicting information. One sensor chain reported instability, another saw normal operation. Automated logic tried to reconcile both, activating compensations that were technically correct but contextually wrong. And because automation was trusted, no one questioned these decisions in real time. Operators noticed patterns that felt strange, adjustments happening more often than usual, systems correcting conditions that did not seem dangerous. But automation had been designed to reduce the need for human judgment. When the system acted, it was assumed to be right. Challenging it meant questioning years of design, philosophy, and millions invested in digital control. There was also economic pressure. Every automated decision was tied to efficiency metrics. Downtime was the enemy. Shutting down a production line for investigation required justification. Data-driven management wanted evidence, not intuition. And the data, filtered through automated logic, kept saying the system was under control. This is the illusion that defines many modern disasters. Not ignorance, but overconfidence. Not lack of technology, but too much trust in it. Automation did not remove human error. It relocated it, embedding assumptions into code, wiring, and logic paths that few people fully understood anymore. By the time the factory crossed into instability, automation was no longer a tool assisting humans. It was the authority. Humans could only react to the consequences. And when systems designed to prevent disasters become the ones accelerating them, the question is no longer what failed, but why no one was allowed to intervene sooner. Because the most dangerous belief inside that factory was not that failures would happen. It was the belief that the system would always save itself. The loose wire sat exactly where no one expected danger to exist. Not inside a high-voltage line, not connected to a critical actuator, not feeding power to heavy machinery. It lived inside a control junction, carrying what engineers classified as a low-risk signal, the kind of component that rarely appears in failure reports because it is assumed to be passive, stable, and predictable. In the original design, that wire had a simple purpose. It transmitted a reference signal between two automated controllers, confirming that a specific operational condition had been met before allowing the next sequence to proceed. It was part of a logic handshake, not a force-driving element. If it failed completely, the system was supposed to stop safely. If it worked, nothing unusual would happen. There was no scenario in the risk analysis where partial failure mattered, and that assumption became fatal. Over time, vibration from nearby equipment caused the terminal connection to loosen by fractions of a millimeter. Not enough to break contact entirely. Not enough to be detected during standard inspections. but enough to introduce intermittent resistance changes. Each micro-movement altered the signal just slightly, creating momentary drops and recoveries that existed in a gray zone between normal and fault. Modern control systems are not built to handle gray zones well. They expect clean states, on or off, fault or normal. When signals behave unpredictably, logic layers begin to disagree. One controller interpreted the signal as noise and ignored it. Another flagged it as a transient anomaly and attempted compensation. A third treated it as confirmation that a sequence should continue. None of them were wrong individually. Together, they created contradiction. Maintenance protocols played a silent role in allowing this condition to persist. The junction panel housing the wire was classified as low priority. It was not part of daily checks, not part of weekly inspections. It was scheduled for review only during major shutdowns. And because the factory had not experienced any serious electrical failures in years, shutdowns were rare and increasingly postponed. There was also the issue of documentation drift. Over multiple upgrades, the system evolved faster than its diagrams. Engineers added layers of automation, rerouted logic paths, and integrated new software without fully reevaluating older physical components. The wire remained in place, performing a role that had subtly changed over time, but without anyone reassessing its criticality. This is how small components become invisible threats, not because they are insignificant, but because they outlive the assumptions they were designed under. What was once a simple confirmation signal slowly turned into a synchronization point between multiple subsystems. When it began misbehaving, those subsystems stopped agreeing on reality. The wire did not fail loudly, it failed politely. It whispered inconsistencies into a system that trusted its own intelligence more than human instinct. Operators saw occasional alerts, but nothing definitive. Engineers reviewing logs saw no clear fault signature. Everything pointed to minor fluctuations, the kind modern systems are supposed to absorb. But absorption has limits. As load increased and operational tempo accelerated, the margin for error shrank. The wire's instability forced controllers to work harder, adjusting more frequently, fighting phantom problems that did not exist. Each correction added stress elsewhere. Each compensation moved the system further from equilibrium. The most dangerous aspect was that the wire was never labeled as a single point of failure. Risk models did not account for partial degradation. Training materials never mentioned it. Emergency procedures did not include it. When the system finally broke down, no one was looking at the junction where the problem started. Disasters rarely begin where people are watching. They begin where assumptions live undisturbed. That wire survived inspection after inspection, not because it was secure, but because no one believed it mattered. And by the time its true role became visible, the factory was already sliding toward a failure that no manual described. In your view, should maintenance protocols treat every component as potentially critical? Or is that expectation unrealistic in complex systems like this? Leave your thoughts in the comments. Long before the disaster became impossible to ignore, the factory was already trying to warn its operators. The problem was not the absence of signals. It was the way those signals blended into the background noise of a highly automated environment. In a system that generates thousands of alerts, metrics, and trend lines every day, subtle anomalies rarely feel urgent. They feel inconvenient. The first signs were not dramatic. A brief delay during a routine startup sequence, a control loop that took slightly longer than usual to stabilize, a motor that corrected its speed more often than expected, then returned to normal. Each event was logged automatically, categorized as non-critical, and buried inside data streams few humans reviewed closely unless something went catastrophically wrong. Operators noticed patterns, not failures. They saw that certain adjustments were happening more frequently during peak load. They saw alarms appear and disappear within seconds. The system was correcting itself exactly as it was designed to do, and that design success masked the underlying instability. One of the most deceptive aspects was consistency. The anomalies did not escalate in a straight line. They appeared sporadically. A quiet shift would pass with no issues. Then a busier shift would show several small irregularities clustered together. This inconsistency made it hard to justify stopping production. If the issue was serious, logic suggested it would be happening all the time. Maintenance teams reviewed reports and found nothing that crossed predefined thresholds. The loose wire was creating micro-interruptions, but each one fell just below the limit that would trigger a formal investigation. The system was failing in fragments, not as a single event, and fragments are easy to dismiss. Human psychology played a critical role. In environments where uptime is rewarded and downtime is punished, people learn to tolerate small deviations. Each successful recovery reinforces confidence. The system corrected itself yesterday. It corrected itself this morning. It will correct itself again. That mindset slowly redefines what normal looks like. Another layer of confusion came from data visualization. Dashboards summarized complex behavior into clean, simplified indicators. Green lights stayed green. Efficiency metrics stayed within acceptable ranges. No single screen showed the growing tension between subsystems. The problem was distributed, and distributed problems rarely look dangerous until they synchronize. At one point, an engineer flagged an unusual pattern during a review meeting. Control responses were becoming more aggressive over time. Adjustments that once happened occasionally were now routine. The observation was noted, discussed briefly, and deferred. Without a clear fault signature, there was no justification to escalate. This is where modern industrial failures often take shape, not through negligence, but through normalization. When systems survive abnormal conditions repeatedly, those conditions stop feeling abnormal. They become part of daily operation. The boundary between safe and unsafe shifts quietly, without anyone consciously deciding to move it. As production demand increased, the system's margins shrank further. Automation compensated faster and harder. Controllers adjusted more frequently. Safety logic remained armed, but it was reacting to distorted information. The loose wire continued injecting uncertainty, and the system continued adapting around it. By the time the final sequence began, the factory had already accepted instability as routine. The warning signs had been seen, logged, discussed, and forgotten. Not because people were careless, but because nothing had yet forced them to stop. And that is the most dangerous phase of any industrial failure. The moment when everyone senses that something is wrong, but nothing seems wrong enough to justify pulling the emergency brake. If you have worked in automated environments, you have likely seen similar warning signs. What do you think makes teams hesitate the most when deciding whether to stop operations and investigate? Deeper, the exact moment the system crossed from instability into disaster was not marked by a single loud event. There was no immediate explosion, no instant blackout, no obvious trigger that operators could point to and say, "This is where it all began." Instead, it started with timing. A precise alignment of load demand, vibration, and automated response that pushed the system past a threshold no one realized existed. As production ramped up, energy consumption peaked across multiple subsystems simultaneously. Motors drew more current. Control loops tightened their response windows. Safety systems remained active, but now they were operating closer to their limits. The loose wire, already unstable, was vibrating more intensely under these conditions. Each micro-disconnection became more frequent, more disruptive, and more confusing to the automated logic interpreting it. In one controller, the corrupted signal was read as a brief fault that required compensation. In another, it was interpreted as confirmation that a sequence should proceed. Two subsystems, both acting correctly according to their programming, began issuing conflicting commands. One attempted to slow a process. The other accelerated a related operation to maintain throughput. The system was no longer correcting a problem, it was arguing with itself. This is how cascading failures truly begin. Not with a single breakdown, but with disagreement. When automated systems lose a shared understanding of reality, coordination collapses. Machines that are designed to work together start pulling in opposite directions. Stress accumulates in places no sensor is watching closely enough. Pressure increased inside components never meant to handle it for long. Thermal readings rose, still within acceptable margins, but trending upward faster than usual. Control software compensated again, unaware that it was amplifying the underlying instability. Every correction pushed another subsystem closer to its own limit. Then the system reached a point where safety logic attempted to intervene. But intervention requires sequence. Shutdowns must occur in the correct order. Valves must close before motors stop. Loads must be reduced before isolation occurs. Because the controllers were no longer synchronized, safety actions triggered out of order. A valve closed while pressure was still rising upstream. A motor accelerated briefly to compensate for what it believed was a loss of output elsewhere. Structural components experienced forces they were never designed to handle simultaneously. This was no longer a recoverable event. Operators saw alarms flood their screens faster than they could read them. Alerts overlapped, some contradicting others. Training did not cover a scenario where the system produced multiple realities at once. Which alarm mattered most? Which action would help instead of making things worse? Every second of hesitation allowed conditions to deteriorate further. Attempts at manual intervention came too late. Automation had already executed sequences humans could not easily reverse. By the time operators initiated emergency procedures, the system had moved beyond controlled shutdown. Energy was trapped in the process, with nowhere safe to go. That is when physical consequences became unavoidable. Structural failure followed logic failure. Components ruptured under combined stress. Containment systems designed for isolated incidents were overwhelmed by simultaneous events. Fire suppression activated in one area while ignition occurred in another. The factory had lost its ability to protect itself. What makes this moment so unsettling is how fast it unfolded. Years of safe operation collapsed in minutes. All the complexity that made the system efficient also made it fragile once coordination was lost. The loose wire did not cause the explosion by itself. It triggered a chain of automated decisions that no human fully understood in real time. This is the hidden danger of modern industrial disasters. They do not escalate gradually in ways that feel dramatic. They accelerate silently, until control disappears entirely. And when that moment arrives, there is no single action that can stop what has already been set in motion. Once the factory crossed into uncontrolled failure, the very systems designed to prevent catastrophe became part of the problem. Automation did not shut down. It accelerated. Controllers continued issuing commands, each one logically correct within its own narrow framework, but catastrophically wrong when combined with others. What followed was not a single malfunction, but a technological feedback loop feeding on its own decisions. Every automated system inside the plant was built with one core assumption: the data it received represented reality. When the loose wire corrupted that data, automation did not question it, it trusted it. Controllers reacted faster and more aggressively, attempting to correct conditions that no longer existed while ignoring the ones that truly mattered. Technology was no longer responding to the factory. It was responding to itself. Redundancy, once seen as protection, became amplification. Backup systems activated not because the primary systems failed, but because they detected conflicting signals. Instead of isolating the problem, redundancy multiplied it. Multiple controllers attempted to stabilize different versions of the same process, each adding its own corrective force. Stability turned into oscillation. Oscillation turned into mechanical stress. One system tried to reduce output to protect equipment. Another interpreted that reduction as a performance failure and increased demand elsewhere to compensate. Load shifted unpredictably. Components that were never meant to carry peak stress simultaneously suddenly found themselves under extreme conditions. Sensors continued reporting data, but that data no longer reflected a coherent system state. At this stage, automation locked humans out. Safety interlocks prevented operators from manually overriding certain actions, assuming automation was responding faster and more accurately than people ever could. That assumption, normally valid, became lethal under corrupted logic. Operators could see the situation worsening, but were forced to watch as systems executed sequences they could not interrupt. The factory effectively split into independent machines, sharing the same space but no longer sharing intent. Each subsystem followed its own rulebook. The coordination layer that once unified them collapsed under contradictory inputs. What should have been a controlled shutdown turned into a chaotic tug-of-war between machines. Heat built rapidly. Pressure surged where flow should have slowed. Emergency cooling activated too late in some areas and too early in others, creating thermal shock. Structural materials weakened under uneven stress. When one component failed physically, its failure fed new data into the system, triggering yet another wave of automated responses. This is the paradox of advanced automation. The smarter the system, the more dangerous it becomes when its assumptions break. Automation does not panic, it does not hesitate, it does not feel doubt, it executes. And when execution is based on flawed information, speed becomes the enemy. By the time humans were able to regain partial control, the factory was no longer a system that could be stabilized. It had become a collection of failures interacting faster than decision-makers could comprehend. Technology had stopped being a shield and turned into an accelerant. This phase of the disaster exposed a brutal truth. Automation can eliminate many types of human error, but it can also eliminate human intuition, judgment, and hesitation, the very traits that sometimes prevent irreversible mistakes. When machines lose context, they do not slow down. They double down. From this point forward, the outcome was no longer about preventing failure, it was about surviving it. When the factory began to collapse from the inside, human operators were no longer decision makers, they were witnesses. Years of automation had reshaped their role, training them to supervise rather than intervene. In that moment, the difference between supervision and control became painfully clear. Inside the control room, operators faced a flood of alarms with no clear hierarchy. Screens flashed warnings faster than they could be acknowledged. Some indicators demanded immediate shutdown. Others insisted conditions were still within acceptable limits. Procedures assumed alarms would appear in logical sequence. They never prepared operators for contradiction. Engineers attempted to diagnose the problem in real time, scrolling through logs, cross-checking values, trying to understand which system was lying. But automation had already moved faster than human reasoning. Decisions that once took minutes were now being executed in milliseconds. By the time people understood one problem, 3 more had emerged. Stress changed behavior. Communication became fragmented. One team focused on stabilizing pressure. Another tried to regain control of energy flow. A third attempted to initiate emergency isolation procedures. Without a shared understanding of what was actually happening, coordination broke down. Everyone was working hard, but not together. Training emphasized trust in automation. Manual overrides were rarely used in normal operation, and many operators had never executed a full emergency shutdown outside of simulations. The real environment was louder, hotter, and more chaotic than any training scenario. Alarms competed with radio traffic. Lights flickered. The system felt alive and hostile. Some operators hesitated, fearing that the wrong action could make things worse. Others acted decisively, only to discover that automation reversed their decisions seconds later. Authority shifted back and forth between human and machine, creating confusion instead of clarity. On the factory floor, conditions deteriorated rapidly. Workers were evacuated as soon as it became clear the situation was unstable, but not everyone escaped immediately. Safety teams moved through smoke and heat, guiding people out while monitoring structural integrity. They were responding to physical danger, while the real cause remained invisible, buried in logic and wiring. The psychological toll was immense. Operators later described a sense of helplessness, of watching a system they once trusted turn against them. They were trained to prevent accidents, yet found themselves powerless at the moment prevention mattered most. This is the human cost of over-automation. When systems fail in ways humans are no longer equipped to handle, responsibility remains, but control does not. People are left accountable for outcomes they could not realistically influence. By the time the final protective barriers gave way, the focus shifted entirely to survival. Containing the disaster, preventing further loss of life, and securing the surrounding area became the only remaining priorities. The factory would never operate again, but for the people inside it, the damage went beyond infrastructure and financial loss. It shattered confidence in systems that promised safety through intelligence. When the automated logic finally collapsed into physical reality, the factory transformed from a controlled industrial environment into a disaster zone within minutes. The failure was no longer abstract or digital. It was violent, visible, and irreversible. What had begun as corrupted signals and conflicting commands ended in fire, ruptured systems, and structural damage that no emergency plan had fully anticipated. The first physical failure triggered a chain reaction. Pressurized components gave way under combined thermal and mechanical stress. A rupture released energy faster than containment systems could absorb it. Flames spread along paths never meant to carry heat, following cable trays, conduits, and ventilation channels that effectively became accelerants. Fire suppression systems activated, but unevenly. Some areas were flooded, while others ignited moments later, overwhelmed by simultaneous failures. Inside the plant, machinery warped and collapsed. Conveyor systems twisted under sudden load changes. Motors burned out as power surged and dropped unpredictably. Control cabinets shorted as heat damaged insulation. The factory floor, once a symbol of precision and order, became a maze of smoke, debris, and broken equipment. Emergency responders arrived to a situation that defied expectations. This was not a single-point incident they could isolate. It was a multi-zone failure unfolding in parallel. Firefighters had to choose where to intervene first, knowing that saving one section might mean abandoning another. Structural engineers warned of collapse risks as heat weakened supports. Evacuation perimeters expanded rapidly. The human toll, while limited by successful evacuations, was still severe. Injuries occurred during the rush to escape. Smoke inhalation, burns, and impact injuries sent workers to hospitals. Psychological trauma followed many of them long after the site was secured. People who had trusted the factory with their safety now carried the memory of alarms, heat, and chaos. Financial losses escalated just as quickly. Production halted instantly and permanently. Equipment worth hundreds of millions was destroyed or rendered unusable. Supply chains dependent on the factory stalled overnight, affecting partners and customers far beyond the site itself. Contracts were breached. Deliveries missed. Entire downstream operations slowed or stopped. Insurance assessments dragged on for months, complicated by the unclear origin of the failure. Was it a mechanical fault, a design flaw, human error, automation failure? Each category shifted liability in different directions. Legal teams became involved before investigators had even finished collecting data. Environmental impact added another layer of cost. Hazardous materials released during the incident required extensive cleanup. Soil and air monitoring continued long after the flames were extinguished. Regulatory agencies imposed fines and demanded remediation plans that would take years to complete. By the time the site was declared secure, the factory was effectively a total loss, not just as a building, but as an operation. Restarting was not economically viable. The cost of rebuilding, redesigning systems, and restoring trust far exceeded the value of what had been lost. What made the aftermath especially painful was the simplicity of the trigger. A single loose wire, an overlooked detail, a failure that never appeared in risk models, yet cascaded into one of the most expensive industrial disasters the company had ever faced. From the outside, the damage looked sudden. From the inside, it felt inevitable in hindsight. The price was paid in steel, smoke, and silence where machines once ran. Once the fire was extinguished and the site stabilized, the real work began. Investigators stepped into a factory frozen in the aftermath of chaos, each damaged component a potential clue. Their task was not just to identify what broke, but to understand how a modern, heavily automated facility could unravel so completely from something so small. The initial assumption pointed toward catastrophic equipment failure. Large systems always draw attention first, but as teams traced events backward, a different picture emerged. Major components had failed only after being pushed beyond their design limits. They were victims, not causes. The origin lay deeper, in the control architecture itself. Data logs became the primary evidence. Thousands of entries showed automated corrections escalating in frequency and intensity in the hours before the disaster. Controllers were working harder than normal, compensating for conditions that appeared unstable but never crossed defined alarm thresholds. Investigators noticed something unsettling. The system had been struggling long before humans realized it. Electrical audits narrowed the focus further. In one control junction, technicians found signs of intermittent contact. A terminal showed uneven wear. The wire connected to it was slightly displaced, not broken, not burned, just loose enough to behave unpredictably. Under vibration, it could momentarily disconnect, then reconnect, leaving behind no obvious trace. That discovery shifted the entire investigation. Engineers reconstructed the signal path and simulated the effects of partial failure. The results were alarming. Under specific conditions, the corrupted signal could cause different controllers to interpret the same state in conflicting ways. Safety systems would activate, but without coordination. Automation would accelerate the failure rather than contain it. Maintenance records revealed how the problem survived for so long. The junction housing the wire was classified as not critical. Inspections focused on high-risk systems and power components. Over time, The factory's rapid expansion outpaced updates to risk assessments. Components that once played minor roles had become central to system synchronization without anyone formally recognizing the shift. Investigators also uncovered organizational failures. Alert thresholds were tuned to avoid nuisance shutdowns. Minor anomalies were filtered out by design. Performance metrics rewarded uptime and efficiency, not cautious intervention. When operators raised concerns, they lacked hard evidence to justify stopping production. Perhaps the most uncomfortable finding was that no single rule had been broken. Procedures were followed. Inspections were completed. Automation behaved exactly as it was programmed to behave. The disaster emerged not from recklessness, but from the interaction of reasonable decisions stacked on top of one another. The final report used language that was unusually direct. The failure was described as systemic, not technical. The loose wire was identified as the trigger, but not the root cause. The real cause was a culture that underestimated small risks in complex systems and overestimated the ability of automation to manage uncertainty. Regulatory agencies responded quickly. New guidelines were proposed, focusing on partial failures, signal ambiguity, and human override authority. Companies across the industry reviewed their own systems, quietly discovering similar vulnerabilities they had never considered dangerous. In the end, the investigation revealed something deeply unsettling. Modern disasters do not always come from dramatic faults. They come from blind spots, from details no one thinks to question until everything depends on them. By the time the final reports were published and the site was officially declared a permanent loss, the industry had already begun to change, quietly at first, then more openly. Because what this disaster exposed could not be dismissed as a rare anomaly or an isolated oversight. It challenged the very logic behind how modern factories are designed, operated, and trusted. The most unsettling lesson was not that a loose wire caused the disaster. It was that the system had no meaningful way to understand uncertainty. Everything depended on clean signals, predictable behavior, and predefined thresholds. When reality slipped into a gray zone, the system did not slow down or ask for help. It accelerated. Engineers reviewing the case realized how many assumptions were embedded into their designs. That low-voltage control lines are harmless. That redundancy always improves safety. That automation can handle complexity better than humans. Each assumption made sense in isolation. Together, they created fragility. One of the key changes that followed was a shift in how risk is defined. Instead of focusing only on catastrophic failures, companies began examining partial degradation scenarios, intermittent faults, signal noise, components that fail politely instead of violently, the kinds of failures that do not trigger alarms but slowly distort decision-making. Maintenance philosophies evolved as well. Components once labeled non-critical were reclassified based on how they interacted with the system as a whole, not just their individual function. Inspection schedules were rewritten. Documentation was updated more aggressively. Assumptions were challenged instead of inherited. Perhaps the most significant change involved human authority. In the aftermath, many organizations reconsidered how much control automation should retain during ambiguous conditions. New designs emphasized graceful degradation, slower response under uncertainty, and clearer pathways for human intervention. The goal was not to remove automation, but to prevent it from becoming unstoppable when it is wrong. The company behind the factory never rebuilt the site. It was cheaper to start elsewhere with a new design philosophy than to resurrect a system whose failure had become a case study taught in engineering programs and safety seminars. The location remains fenced off, a quiet reminder of how quickly order can turn into collapse. What makes this story resonate is its simplicity. No explosion caused by reckless behavior, no dramatic sabotage, just a small, ignored detail living inside a system that trusted itself too much. A reminder that complexity does not forgive assumptions, and that efficiency without vigilance carries a hidden price. Modern industry continues to push toward faster, smarter, more autonomous systems. And somewhere, right now, there are factories running perfectly, dashboards glowing green, small anomalies being logged and forgotten. The lesson from this disaster is not to fear technology, but to respect its limits, because the next failure will not announce itself loudly. It will arrive quietly, hidden behind the belief that nothing so small could ever matter. If you stayed until the end of this story, you already understand how fragile even the most advanced industrial systems can be. Take a moment now and leave a comment below, writing "small details matter," to show you made it all the way through and to share your awareness of how these disasters really begin. If this analysis helped you see industrial safety and automation from a deeper perspective, make sure to like this video and subscribe to the channel for more real investigations into catastrophic failures, hidden risks, and the lessons industries often learn too late. And don't stop here. The next video appearing on your screen dives into another industrial disaster where a single overlooked assumption led to devastating consequences. Click it now and continue the story.